Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Introduction to Magnetism from the paper Functional Materials. The main points which will be covered in this module are: first, the basis of magnetism in the materials is discussed. Second, diamagnetism, paramagnetism, ferro and ferrimagnetism are also discussed. Switching in the ferromagnetic materials leading to magnetostriction is also discussed in this module. Ferromagnetic and their examples have also been discussed. Magnetic ferrites and their applications are also discussed in this module. So students, let us start with a basic introduction about this module. Magnetic ceramics are important materials for a variety of applications such as data storage, tunnel junctions, spin wells, high frequency applications, etc. These materials possess extraordinary properties such as strong magnetic coupling, low loss characteristics, and high electrical resistivity, which is often related to their structure and composition. Depending upon the type of application, based on the knowledge of materials, one can choose the appropriate material. So, to build an understanding, we first have a brief look at the basics of magnetic properties, followed by the various types of magnetism in the materials and key characteristics and differences. This will be followed by a discussion on magnetic ceramics with their emphasis on some of the key applications. Applied magnetic field. The figure shows current which has been created by applying a magnetic field through a coil. A current is flowing through the coil and a magnetic field is applied through the coil having n turns in total, and L is the length of each turn. Hence, according to Ampere's circuital law, when a current flows through a coil, it gives rise to a magnetic field in the direction perpendicular to the plane of the loop. The field is related to the current by the equation H is equal to Ni, or we can say that the relation between the applied magnetic field H and the current is H is equal to Ni by L, where L is the length of each turn. Response of a material. When a magnetic field is induced in the material, then B is known as a magnetic induction has been introduced inside the material, and the unit of B is Tesla, and a B is related to H by the equation as B is equal to mu naught H. Origin of magnetism. So students, as we have already discussed that the magnetism has been introduced, or the origin of magnetism is basically due to three components, or we can say we have primarily three moments. First is the orbital moment, as shown by the figure that an electron is orbiting around the nucleus having a fixed radius, having an orbital moment represented by mu m. Secondly, we have a spin moment, which is also shown by the figure that an electron is spinning around its axis, having the spin moment represented by mu m. Third is the change in the orbital moment by the changing magnetic field, which is clearly depicted in the figure. So let us discuss the source of magnetism. Basically, we have three sources of magnetism. First is the motion of electron in an orbit of an atom. Second, spinning of electrons around its own axis, that is, spinning gave rise to the moment. Third, nuclear magnetic moment, which is insignificant in the context of most magnetic materials of practical interest, and it can be neglected. So students, let us discuss about the magnetic moment. Magnetism in the materials is crudely explained as mutual attraction between the two pieces of the material, say iron or iron ore. There are various microscopic mechanisms of magnetism in the materials. The strength of the magnetism is quantitatively judged by a quantity called as magnetic moment. This magnetic moment should not be confused with the dipole moment, as we have learnt in the dielectrics. The major contributors to the net magnetic moment in a material are: first, the orbital moment, which arises from the motion of electrons in the orbit of an atom. Orbital moment can be related to the current which is flowing in a loop of a wire of zero resistance. Second, the spin magnetic moment due to the spinning of an electron around its own axis. Third is the nuclear magnetic moment, which is due to the nuclei, which is rather insignificant in the context of most magnetic materials of practical interest, and it can be neglected. First two contributions, they are quite significant, and they contribute to most of the magnetic character of a material, while the third component, that is nuclear magnetic moment, is rather insignificant in the context of most magnetic materials of practical interest, and it can be neglected. The orbital moment. So students, here we will be discussing about the relation between the orbital moment and the current. Let us consider an electron which is rotating in an orbit around the nucleus, and the radius of the orbit is r. Let us represent the orbital moment by mu m orbit, which is equal to A multiplied by current, where A is the area of cross section and I is the current. As we know that the area is equal to pi r square, that is the area of a circle. And now let us evaluate the expression for the current. Now, based on classical physics, the current I is nothing but the charge per unit time, and it is expressed as I is equal to Q by T. The time is nothing but the circumference divided by the velocity of an electron v, that is T is equal to 2 pi r by v, which is substituted in the equation for the current to yield I is equal to qv by 2 pi r. Now putting the value of I in the expression of orbital moment, we get mu m orbit is equal to pi r square multiplied by q multiplied by v by 2 pi r, and this has been simplified to qvr by 2. Hence, now putting the value of q, we get mu m orbit is equal to minus e by 2m multiplied by mvr. Here we did the division and multiplication by m. Hence, finally, we get mu m orbit is equal to minus e by 2m multiplied by j, where j is the angular momentum of an electron and it is equal to mvr. As we saw earlier, spinning of electron about its own axis also give rise to a moment. For purely quantum mechanical reasons, for an electron spinning around its own axis, the ratio of spin magnetic moment to angular moment is twice as large as for orbital moment. That is, the spin moment, that is mu spin or mu s, is equal to minus e by m multiplied by j spin. Now we will be discussing the total magnetic moment having the contribution from the orbital magnetic moment and the spin magnetic moment. The net magnetic moment for an atom containing several atoms is basically the net sum of these two contributions. That is, mu net is equal to mu net orbit plus mu net spin. Although it is not possible to explain classically from quantum mechanics, the ratio of net magnetic moment to the angular momentum always works out to be between 1 and 2. This is related by a factor called as Landé's G factor or G, purely because net moment is the sum of these two and can be expressed as mu net is equal to minus G multiplied by E by 2m multiplied by J, where J is the summation of L plus S. Here, the value of G would be 1 for purely orbital moment and it is 2 for purely spin moment. Latter is true for many ferrites where orbital magnetic moment is thought as quenched and the dominating contribution to magnetic moment arises from spin magnetization. Now, the value of G can also be evaluated by L, S and J, and it is given by G is equal to 1 plus J multiplied by J plus 1 plus S multiplied by S plus 1 minus L multiplied by L plus 1, the whole divided by 2J multiplied by J plus 1. Again, quantum mechanics argues that the angular momentum can take only certain values which are defined by orbital and spin quantum number small l and small s respectively. Hence, the angular momentum for an electron with a characteristic number small j is expressed as capital J is equal to root of small j multiplied by j plus 1. This whole is multiplied by h bar, where h bar is equal to h by 2 pi and h is the Planck's constant. The characteristic number j can be orbital quantum number. L is for purely orbital moment and S is for spin quantum number for spin moment. Since magnetic moment is now quantized as a result of angular momentum being quantized for an electron, we can define a basic quantum unit of magnetic moment as Bohr magneton, mu b as mu b is equal to E h bar by 2m, and the value of one Bohr magneton is 9.274 multiplied by 10 to the power minus 24 ampere meter square. Mu m is equal to minus g mu b multiplied by J. Nuclear magnetic moment is only of the order of 10 to the power minus 3 mu b and hence is neglected for most of the cases. Macroscopic view of magnetization. We define magnetic induction, that is B, as mu naught H, where mu naught is the magnetic permeability of vacuum and it is equal to 4 pi multiplied by 10 to the power minus 7 Henry per meter, and the unit of B is Tesla or Weber per meter square. This also explains that while H depends only on the current, B also depends upon the medium which is surrounding the wire, that is represented by mu naught. Now, rewriting equation B is equal to mu naught H yields B is equal to mu naught Ni. Now imagine if a magnetic material is inserted within the coil, then there is a current which is induced in the magnetic material too, which is called as Amperian current, represented by IA. Thus, if we will modify the above equation as B is equal to mu naught Ni plus mu naught Ia. Now we rewrite this equation as B is equal to mu H. The Amperian current Ia in the magnetic material can be replaced with induced magnetization M, and thus we can write B is equal to mu naught bracket H plus M. If magnetization is assumed to be proportional to the magnetizing field H with proportionality constant, which is defined as magnetic susceptibility, that is chi m. M is equal to chi m multiplied by H. Hence, we can write B is equal to mu naught bracket H plus chi m H. And taking H common, then B is equal to mu naught H multiplied by 1 plus chi m. Or we can write B is equal to mu naught mu r multiplied by H. Now we can write mu is equal to mu naught mu r, where mu r is the relative permeability. Here chi m is similar to dielectric materials, and it can be thought of as a parameter which expresses the magnetic response of an electron in a material to the applied magnetic field and is a dimensionless quantity. Here mu r is equal to 1 plus chi m is the relative permeability of the material in a similar manner to the relative dielectric permittivity epsilon r. In general, both susceptibility and permeability are tensors, and assuming that vectors are collinear wherever there is a vector notation is not used. Now students, let us discuss about the magnetic susceptibility or chi m. First of all, chi m is a dimensionless quantity. It measures the material response relative to the vacuum. Chi m is nothing but the ratio of magnetization divided by the magnetic field intensity. Hence, if we will plot a graph between the B versus H, then chi represents the slope of that straight line. Naturally, for vacuum, chi m is equal to 0. However, unlike dielectric materials, chi m can acquire a positive and negative values. Types of magnetism. Magnetic materials can be classified based on the values of magnetic susceptibility. As we can see from this expression that B is equal to bracket 1 plus chi bracket close mu naught H, where chi is the magnetic susceptibility. So, depending upon the value of the magnetic susceptibility, we can classify the materials into 3 magnetic materials. First is diamagnetic, second paramagnetic, and third is ferromagnetic and ferrimagnetic. Materials with negative susceptibility are diamagnetic materials, and they have the chi-m to be less than 1. As we can see from the graph that for diamagnetic materials, chi is approximately minus 10 to the power of minus 5. Most diamagnetic materials shows very small negative susceptibility except the superconductors in superconducting effect where chi-m is equal to 1. And this property is very useful for applications such as magnetic levitation. Other diamagnetic materials are Al2O3, copper, gold, silicon, silver, or zinc. Next is paramagnetic. Paramagnetic materials, which is represented by the graph 2, have the magnetic susceptibility to be equal to 0. And the materials which exhibit the paramagnetic behavior are aluminium, chromium, molybdenum, sodium, titanium, and zirconium. Next is ferromagnetic. Susceptibility is positive but very small for paramagnetic materials, but it can be very large for ferro and ferrimagnetic materials. The examples for ferromagnetic materials are Fe3O4, NiFe2O4, and the examples for ferrimagnetic materials are ferrite, cobalt, nickel, having a very large magnetic susceptibility as 10 to the power 6. Susceptibility of common materials. The table shows the values of susceptibility for the 3 types of magnetic materials, that is diamagnetic, paramagnetic, and ferromagnetic. It also tabulates the values of nu. As evident from the table that for diamagnetic materials, the susceptibility is very small, that is of the order of 10 to the power minus 6, and it is negative also. Whereas for paramagnetic materials, the susceptibility is still the small, but it becomes positive. Whereas for ferromagnetic materials, susceptibility is very large and it is a positive quantity. It should be noted also that except for diamagnetic materials, magnetic susceptibilities are temperature dependent. Signs of susceptibility can also be related to the penetration of magnetic flux inside the material. This says that for diamagnetic materials, when an external field is applied, the magnetic moment that is induced is in opposite direction to the field direction. That is, it shows the opposite magnetization. This is an inherent effect which is present in all the materials. It is just that some materials like silver, gold, silicon are only diamagnetic, that is, they don't have any other effect present in them. In many other materials, on the top of diamagnetic effect, which is inherent to all the materials, other effects are present which contribute significantly to the magnetization, and all of these tend to have induced magnetization, that is in the direction of applied magnetic field, they exhibit the positive susceptibility. This means that magnetic flux penetrates into the material. Now we will discuss these effects one by one. This figure shows the flux penetration in magnetic materials with various ranges of susceptibilities. In a nutshell, net susceptibility of a material is the sum of all types of magnetic contributions. For materials having only diamagnetic contribution, this turns out to be negative. Moreover, it is quantum mechanics which shows that materials are diamagnetic or ferromagnetic or paramagnetic. If we taken too far, classical mechanics simply shows that all the magnetic moments in any material cancels out. Now coming back to the diagram, here A and B represents that the magnetic field lines for a para and a ferromagnetic material. It shows that the response of the material adds to the external magnetic field due to a positive magnetic susceptibility. The C part shows a normal diamagnetic material with weak opposite magnetic response, and D part shows a perfect diamagnet with equal and opposite induced magnetization, having magnetic susceptibility to be equal to -1. The example for this state is a superconductor. So students, let us summarize what we have learned in this module. First, the magnetism in the materials arises due to the orbital and the spin magnetic moments. Second, the response of a magnetic material upon the application of an external magnetic field is represented by magnetic susceptibility. Third, based on the sign and the magnitude of susceptibility, the materials are classified into 4 categories. First is diamagnetic, second paramagnetic, third ferromagnetic, and fourth is ferrimagnetic. Thank you.